The oscillatory dynamics transductive bridging theorem begins with a specific premise about the universe. At its base layer, reality is not made of discrete particles, but an undifferentiated scalar coherence field. Within this framework, physical entities, anything that possesses a recognizable state, do not exist independently. They are emergent properties of the field, dictated entirely by a mathematical relationship known as the identity function. The mechanics of this emergence are written in the identity function. C sub n equals the sine of f times delta phi multiplied by the cosine of nu times RCR. The equation breaks down into two distinct forces. The sine term represents active phase strain. This is the tension in the system, the inherent drive toward change and instability. The cosine term carries the coherence memory. This dictates the system's persistence, its stability, and its resistance to being altered. Observable physical identity only materializes through the precise multiplicative coupling of these two elements. Without both tension and stability acting together, there is no identity. To understand how the first identities form, we have to isolate the z equals 0 boundary. This is the vacuum state before any identity exists. Here, the system carries zero phase strain, but holds maximum coherence memory. When we evaluate the identity function specifically at these z equals 0 conditions, the sign of 0 evaluates to 0. This creates a mathematical product 0. The observable identity equals 0 because the sign factor vanishes. But the cosine term, the coherence capacity of the field, remains strictly non-zero, designated by k. Because the vacuum holds capacity, we can map the exact boundary where it breaks. We need to investigate the emission lock manifold at the precise moment the system departs from z equals 0. The math tells us the vacuum is not empty. It is a structurally pre-emission environment, holding maximum capacity, waiting for the strain required to project it into reality. The rules governing where identity can form are dictated by the two emission lock conditions, derived directly from the field equations of the recursive scalar Lagrangian stack. We can test the vacuum state by substituting a phase strain of 0 into the lower lock condition. Mathematically, this immediately forces the system's recursive coherence memory to 0. Take that 0 memory value and substitute it into the upper lock condition. The cosine results to 1, and the equation collapses to 0 equals negative beta times f. Because our starting parameters are finite and non-zero, this is a strict mathematical contradiction. The direct consequence is absolute. The two emission lock conditions cannot be satisfied simultaneously at the origin. We have proven the vacuum exclusion theorem. The undifferentiated field is structurally excluded from the emission lock manifold. Physical identity cannot form without an initial phase strain to trigger the equation. Since the absolute zero state is locked out, we must analyze the system at its very first permissible departure, an infinitesimal step away from the vacuum boundary. As the phase strain perturbation approaches 0, we apply small angle approximations to the lock conditions. The complexity strips away, and the two constraints linearize. They collapse into this transcendental base state equation. Notice that the entire structure of the solution is governed by a single dimensionless parameter, c, which is the product of beta, f, and nu. The solutions to this equation define the allowed ground state configurations. They provide the specific set of memory values where the field can achieve stability as it moves away from 0. This chart is the z equals 0 attractor topology map. It plots the numerical solutions to our base state equation as the coupling product c increases along the horizontal axis. In the upper panel, watch the behavior of the solutions. As c increases and hits the first critical threshold, the line undergoes a tangent bifurcation. Two entirely new stable solutions emerge simultaneously. The lower panel tallies the total number of accessible states. The bifurcations force the system into a rigid step function. It progresses in a strict odd number hierarchy, from 1 allowed identity to 3 to 5 to 7. As the coupling product scales up, the mathematical spacing between these spontaneous bifurcations shrinks, converging rapidly toward exact multiples of pi. The Lagrangian dictates a discrete, hierarchical attractor topology at the vacuum boundary. The physical universe generates new ground states on an exact, repeating, pi periodic schedule. We can frame this mechanism using established physics, the Landau-Ginzburg framework and the mean field Ising equation. This chart places the Ising mean field model side by side with the ODTBT base state. Structurally, they are isomorphic. Both rely on self-consistent fixed-point equations to break system symmetry and generate new states. But look at the red graphs on the left. The Ising model uses a monotonic hyperbolic tangent function. Because of this shape, it triggers exactly one pitchfork bifurcation, hard capping the system at a maximum of 3 states. Now look at the blue ODBTB graphs. Our base state equation uses an oscillatory cosine nonlinearity. As it cycles, it triggers an infinite cascade of periodic bifurcations. Plotting the full nonlinear constraints on the emission lock surface verifies the stability of these solutions. In the right panel, the intersecting lines isolate into exact star-shaped points. The emission lock manifold consists of distinct coordinates, not fluid curves. The Ising model reaches a ceiling at 3 ground states. Because the ODTBT equation is oscillatory, it supports a potentially unbounded hierarchy, a mathematical structure capable of accommodating the vast diversity of the periodic table. We now have a theoretical topology where physical states unlock in sets of 2, gated by thresholds separated by intervals of pi. We observe this exact discrete progression in acoustic mechanics. As drive amplitude increases on a physical Chladni plate, random noise doesn't smoothly transition. It snaps into complex geometric eigenmodes at strict resonant thresholds. This provides a clear, testable prediction for the lab. If repeated training cycles alter the memory stiffness of the field, the variable mu sub rec, the exact coupling thresholds required to reach new ground states will predictably shift. And we already see that amplitude limits required to trigger cymatic patterns depend on frequency. This physical dependency structurally maps back to the coupling-dependent bifurcations inside the base state equation. The derived eigenvalue spectrum serves as a direct mathematical mirror for the acoustic resonance we can measure in the real world. To evaluate this framework properly, we must isolate what is mathematically proven from what's yet to be observed. The pi periodic cascade is a structural property of the equation itself. However, the 3 components of the coupling parameter C, beta, f, and nu, are currently dimensionless. They describe a ratio, but they are not yet mapped to standard physical units. This cascade structure was not artificially imposed to fit external data. It was discovered internally. It is a strict, inescapable consequence of evaluating the Lagrangian at its own zero-point boundary. The question we are left with is empirical. Does the pre-emission vacuum of our physical universe actually operate according to this specific cosine modulated potential? The internal logic of the math is rigorous. Proving it governs reality requires the next era of laboratory experiments to map these constants to measurable physics.